Okay, so welcome everyone to the NPA seminar on a Wednesday. We're happy to have Ryan Plestid here to tell us about beta decay. So Ryan did his undergrad at the University of Guelph and moved to McMaster University for his master's and PhD in 2017, and then moved to postdoc at Fermi Lab in Kentucky, and has now moved on to a neutrino theory network fellowship at Caltech. So he's going to be telling us about some of the maybe exciting new theory that's going into possibly causing tension in the CKM matrix topper.
Great, thanks. So yeah, I'm going to tell you about some new work, these 4 papers on QED corrections to beta decay, and how to set this problem up by using effective field theory thinking. So this is work in collaboration with Richard Hill. Kaushik is on the second or the third of the listed papers. And the last paper is kind of a little result that's used in the third paper. I'm not going to talk about it much, so I'll just kind of advertise that at the beginning. I pulled it out to kind of give more time for introduction. And but it's just a technical tool for reducing the number of diagrams you actually have to compute. That's kind of cool. And it generalizes some old tricks that were known for when you just have a heavy particle going through a diagram to when you have a charged current. So the main novelty of that work is that when you have a weak interaction, the charge of your heavy object actually changes. So like the incoming particle is different than the outgoing particle. And so that means you can't think of everything as a static Coulomb field. And so this basically systematizes how to compute corrections to the limit where you could think of this as like a background Coulomb field over nucleus. Okay, so the beginning of the talk, I encourage you to ask as many questions as you wanted. And obviously throughout the talk, I'm also happy to field questions. We don't need to get through everything, but this is the rough outline of the talk. Okay, so I'm going to try and convince you that super loud beta decays, or beta decays more generally, are relevant for fundamental physics. So I'm just going to use one very simple example, which is measuring CKM matrix elements using super loud beta decays. There are other applications of precision beta decay that are interesting. I'm going to be talking about ordinary beta decay, so not double beta decay or neutrinoless double beta decay, just standard beta decay. And the idea is if you measure it very, very precisely, you can learn something interesting. Okay, so for some of these beta decay experiments, you need a lot of precision. And what that ends up meaning is that you need to compute, for some of the corrections, you need to compute loops, like you'd learn in a quantum field theory class. Okay, and the loops are going to come from exchanging photons between the outgoing positron or electron and other charged particles in the reaction. Okay, and so in beta decay, you have a lot of different scales. So you kind of start from the W boson mass, and you integrate that out. So you can think of an effective theory with a point-like contact interaction. But you also have other scales in the problem. So you have the nuclear radius, you have the energy of the outgoing electron. And effective field theory is a very useful theoretical tool for dealing with problems where you have so many different scales floating around. Okay, so let me just give you a sketch of how you measure this CKM matrix element using super loud beta decays. So VUD, for those who haven't thought about this, basically tells you how strongly up quarks couple to down quarks via the charge current. Okay, so if you have anything where like a neutron becomes a proton, right, that matrix element has to be proportional to VUD. And it's important to measure these CKM matrix elements because you can test certain things about the standard model. Like if we really just have 3 quarks and no new physics, then the CKM matrix should be a unitary matrix. So that means there's a number of different relationships that you can test if you can measure all the elements of the CKM matrix very precisely. So what I want to show you, this comes from a review by Hardy and Towner. So they've been doing these reviews, I think, since the late or sometime in the 80s, in which they compile all of the measured decay rates of a bunch of super loud transitions. Super loud means spin 0 and positive parity transitions to spin 0 and positive parity. And the reason why I'm showing you this is just to show you how small the uncertainty is on this quoted number of VUD. Okay, so it's at the level of 6 times 10 to the negative 4. So this is kind of either a very impressive or very insane level of precision, right? You might even be suspicious if you're dealing with a nucleus that you could ever achieve this kind of theoretical control. Okay, so the basic questions I want you to ask are like, if we're talking about CK and unitarity, are all the theoretical errors really under control? And what's really needed if I want 10 to the negative 4 precision? So I think maybe point 2 is like a useful exercise to go through whenever you look at a precision physics paper. So can you just take a step back? If somebody says, I want to measure that and make an inference about fundamental physics at this level of accuracy, you should be able to come up with in advance all of the effects you need to include, right? And to what order, and if you can find small parameters, you should be able to figure out to what order in an expansion you need to work to. Okay, so just to give you some intuition about why you need to measure VUD so precisely for certain interesting tests of new physics. So famously, the CKM matrix is mostly diagonal. So what that means is that VUD is much, much bigger than VUS, which is much, much bigger than VUD. So if you want to retest this relationship, right, I need to look for this number squared plus this small number squared, right? Is that equal to 1? This number is so small you can basically neglect it. Okay, so basically first row CK unitarity comes down to testing these two numbers and seeing if when I square them, right, the absolute values, do I get 1? And if you don't get 1, and you're really confident in your theory, this is a bona fide sign of new physics. Okay, so the reason why this is, you have a more challenging precision goal for VUD is simply that I need to measure this quantity, right, to a level of accuracy that's comparable to how well I measured this quantity. So if I measure VUS to 1%, I need to measure VUD to about 10 to the negative 4. Just because VUD is about order 1, whereas VUS is already at leading order, kind of down by this small number. Okay, so if you want to test CKM unitarity and you have percent level data from kaon decays, you really need this high level of precision for VUD. Okay, so why would you use superlab beta decays? So there are other options. You could use neutron beta decay. There's an unfortunate fact that we have 2 different measurements of the neutron lifetime and they don't agree. Okay, so maybe that's out for now until that discrepancy can be resolved. You could use pion beta decay, but it's harder to measure pion beta decay. The statistics are lower, okay? Superlab beta decays have a huge advantage in that there's lots of isotopes, right? They're easy to make in large numbers, and you can measure many of them. You don't have to live and die by just one species. However, none of that would matter if this all relied on some nuclear matrix element that you needed to calculate. So the magic of superlab beta decays is that you don't need to calculate a nuclear matrix element. Okay, so the magic is that if you have a 0 plus to 0 plus transition, then only the vector current contributes. Okay, so that's just some selection rule that applies in the limit of when a nucleus has a small radius relative to the Q value of the reaction. If only the vector current contributes, that's important because the vector current is very nearly conserved in the standard model. Okay, you can check this. This just depends on the size of quark masses. Okay, now if the vector current is conserved, then its matrix elements are not renormalized. Okay, and if you have isospin symmetry, then what you find is that you can relate the transition you want to measure, which is some, okay, these should be flipped around. I don't know why I did this. Some initial state A going to final state B via this tau plus operator, okay, which is just changing the charge of the nucleus. Could be tau plus or minus. And you can just relate this using the Wigner-Eckhart theorem to some reduced matrix element, okay, where because these states, A and B, if they have a different number of neutrons and protons, they're related by isospin symmetry. That means that I can reduce this to some reduced matrix element of the identity between the states A and A, right? And this is just clearly 1. Okay, and so you're just reduced down to a Clebsch-Gordon coefficient that came from using the Wigner-Eckhart theorem. So this is kind of the magic of why this all works. And then you just have to ask, okay, well, there's clearly corrections to these things. Maybe the vector current isn't perfectly conserved. Isospin symmetry is broken. And then also, importantly, quantum electrodynamics breaks isospin. And that means that whenever I have radiative corrections from photons talking between the electron and the nucleus, I get corrections to these things. So there are a number of things you need to consider. So power corrections are not zero. So what that means is this selection rule that only the vector current contributes, that holds in the limit that of QR is small. So if the nucleus, you take into account that it has a finite radius, there's power correction. Isospin is not an exact symmetry of QCD, the underlying theory. So sometimes people call this explicit isospin violation. And then the Coulomb interactions inside a nucleus, the fact that there's a bunch of protons and they're all pushing on each other, but neutrons are not pushing on each other via the Coulomb interaction, that also breaks isospin. All three of these things are important, and they're not what I'm going to talk about today. I'm going to focus on this part. I would argue that of all of these things, this is probably, actually these two items are both very important. This is, I would say, basically taken care of. And this is an active area of research. So there are estimates of the isospin breaking from the Coulomb interaction, but you can ask if they've been done properly. And people who do nuclear ab initio are kind of working on this. There are also nuclear ab initio aspects of this problem, but I'm going to talk about some part of the problem that doesn't depend on nuclear theory.
So is there any intuition to understand which effect would dominate?
Good question. I don't know. I don't know if there is like a easy intuition, but the way you go about doing this is you ask what parameter controls the breaking of each of these effects. So maybe we can just go through that. Power corrections, I can, are there markers I can write with? You guys are all surprised.
Nobody does this. Here. We never have this kind of request.
Okay, so thanks. Oh, there's markers right here. So power corrections. You can tell that nobody writes with these because they're really good. Okay, so power corrections are controlled by PR. So PER. Okay. So this is a limit that you can think of it like the multipole expansion. You're just expanding like in the point-like limit, right? So if I took the radius of the nucleus to 0, everything needs to behave like a point-like object. So that means that that's what controls these parameters. Okay, or these corrections. There are isospin breaking corrections. Let's call it delta, or maybe I used words here. I don't think I have a good. So these break up into two different things. So one of them is easy. It's controlled by quark masses. So it's basically m up minus m down over roughly 1 GeV. This is this explicit isospin break. Okay. Now, for the intranuclear Coulomb repulsion, I don't actually think I can give you a nice parameter. I don't know that off the cuff, but it's going to have to go something like the number of protons in the nucleus, maybe squared, times alpha, and let's just guess that it's that. But importantly, it has to go like that squared. Okay, so there's some theorem. Actually, both of these things have to go like this. There's a theorem that says that all isospin breaking corrections vanish at leading order. It's called something Gatto theorem, Adolemo Gatto or something. Okay, so there's a theorem about that. Radiative corrections, this will actually be important for the talk. So naively, this is easy. Okay, particle physicists who compute loops and are worth their salt will know this. The natural power counting parameter is alpha over 4 pi. And that 4 pi matters, so that's 10, right? So, and that's every order in the expansion comes with an extra factor of 1/10. That makes this quite small. But you can pick up logs when you go to compute this. Okay, so let me just, let me say that the biggest effect you could get is something that goes like alpha over 4 pi times some log. So this could be like log, to make this concrete, me times the radius of the nucleus. Okay, so in this case, the mass of the electron is very small compared to the inverse nuclear radius. Okay, so this is a, maybe I'll do absolute value. This is a number that's maybe like 5 or something like that. Okay, but it can show up at every order in the expansion. So you can get log squared, you can get, okay, so let's keep track of that. So this is true when I'm coupling to charge 1 particles. But you have a nucleus in the reaction, right? So more generally, actually, there's another expansion parameter, which is Z alpha with no pi's. And this is coming from interactions where you couple coherently to the entire nucleus. And the whole point of actually what I'm going to talk about is that counting this Z properly and understanding how everything related to the Coulomb field of the nucleus is kind of an involved problem. And that's kind of what all these papers are about. It's about the fact that you get a bunch of leading Coulomb stuff. So actually, just by a show of hands, because this will help. So how many people know or are familiar with what the Fermi function is in beta decay? Okay, so I'll spend some time discussing that. So the largest of these effects, all the leading ones, are included in something called the Fermi function. But there are further corrections that involve things you can have a correction. So now that you've identified all this, right, you can, so this power counting parameter for the super loud beta decays is like maybe 1/10. So it's 0.1 is not that small. This, by contrast, is like 0.02 or 0.002, 2 times 10 to the negative 3. This is a much smaller number. Okay. There are also, I'll say there's another thing I'm neglecting here. People will talk about recoil corrections. So recoil, what they usually mean is the Q value of the reaction divided by 2 times the nucleon mass. So this is also about 10 to the negative 3, just like MEV over GE. Okay. So you just have to go through, and you can see this kind of starts to get a little complicated, and imagine expanding your amplitude in like a multiple power series in all of these small numbers. And so there's a well-defined notion in which you can just ask, like, which of the coefficients do we know? And which ones should we know if we want to claim that we've actually computed things to a level of accuracy that are needed in, for the experiment. So I'm going to be talking about these ones. Yeah. So the maybe to answer your question, like this is 0.1. This should be like maybe a 1% effect. So 0.001. This is 10 to the negative 3. Right. So once you know the size of these power counting parameters, you can quickly estimate which terms you need to keep and which ones you don't. But I don't think there's any intuitive reason why, because it just comes down to what are the scales of nature, right? It's just that Q values are small compared to the mass of nucleons. And so for each of these, I can give you an intuitive explanation, but the relative size of all the terms, it just comes down to what the fundamental constants of nature are. Okay. So don't worry, I'm not going to ask you to keep track of all those things during the talk. Okay, so let me just describe how these radiative corrections work historically. So I'm going to ignore almost everything except for the radiative corrections. This is isospin breaking actually here, but this is what you'll find in Towner and Harvey. So what does this mean? This funny big FT basically means the decay rate of a nucleus. Okay, this little FT is this thing that I'm going to talk about in a bit called the Fermi function. Okay, so this is basically the wave function of an electron evaluated at the nuclear inside the nucleus. So the picture is that the Coulomb field will enhance the probability that an electron is near the nucleus, and therefore it increases the rate at which you would emit electrons. It's easier to create an electron from a vacuum when you have a Coulomb field. Okay, by way of contrast, if you have a positively charged particle, it's repelled from the nucleus. It doesn't like to be there. And so it decreases the probability that you will emit a positron. Okay, So that's a large effect. It's been known since like 1934 that this is a thing. That's why it's called Fermi function, because it's Enrico Fermi wrote a paper. Okay. However, in addition, there are these other subleading radiative corrections. That means they're down by a power of alpha over 4 pi. Okay, and those are these, and those corrections people decompose into different terms. So there's something called the outer corrections. These are supposed to be long distance things. There are corrections that depend on nuclear structure. So they're not you're not going to take the short distance or the point-like limit. There are corrections related to isospin breaking. And then there are these corrections, people call them inner corrections, and those come from loops where you're really talking about where you're probing the inner structure of, say, the W boson or the constituent quarks that make up a neutron. So just as a cartoon, you can roughly compute these using perturbative QCD and like just Feynman diagrams. Okay, there's a bit of an art to how to deal with when you get down to scales of order the proton mass. There's been a lot of work on this from some people at Los Alamos and the INT. Okay, so there's been progress on this. Nuclear structure stuff, you need a model of a nucleus, and there's a group at Triumph that's actively doing this, and a group at also collaborating from Valencia and INT that's doing this stuff. All this is what I'm going to be talking about. Okay, but the important thing I want to emphasize here is both the Fermi function and these radiative corrections come from photons. They're both really radiative corrections. Okay, even though historically the way people talk about them as separate, okay, at the end of the day, if I turned off alpha, the Fermi function just becomes 1. Okay, it just the effect just drops out. So both of these are really long distance effects that are related to the exchange of photons. And so they should really be treated together. Okay. So what I'm going to try and tell you in the talk, I'm going to try and sketch what is this Fermi function, how is it traditionally defined, and what's it really mean as an object that you would compute in quantum field theory, and how do you deal with this interplay of radiative corrections in the Fermi function. Okay, so the Fermi function heuristically is this. So this is just the wave function of an electron evaluated at some point x. And I just evaluate at some x that's close to the nuclear radius. But there's a problem with doing this, which is that this thing is divergent as I take that radius to 0. So the historical workaround was we'll just evaluate at some radius r. And then later we'll actually solve the full Schrodinger equation Dirac equation with a nuclear potential. But when you want to interface with higher order radiative correction, it gets very confusing very fast. You have one way of dealing with this where you solve a wave function, and when you go to compute the radiative corrections, you're computing diagrams. So you'd like to see both of these things emerge from the same place. Okay, so I think I mentioned this already, but when you have a diagram like this, so this is supposed to be a heavy nucleus, goes to another heavy nucleus. There's a neutrino coming in, but you could just make the neutrino go out, and there's an electron. And when the momentum flowing through this photon is kind of large enough that, long distance enough that the nucleus, oh, this doesn't show up on the screen. There's supposed to be a nucleus here that's very tiny. Okay, then you're in the limit where the wavelength is large compared to the radius, and you couple to the whole charge of the nucleus. Okay, so basically for long distance regions, alpha can become Z alpha when photons talk to the nucleus. You had a question?
So just so I understand, so the weak interaction is just Fermi, it's like 4-point interaction. And then you're calculating corrections with QED.
That's correct. That's right. Yeah, so that's like a contact interaction. And then I'm just drawing graphs that where I take a photon and it can come off of the electron line because the electron is a QED field, and it can attach to the nucleus. Now you might actually have some confusion. How do I do a nucleus in QED? I never learned how to do that in my class. Like I learned how to do a muon and an electron.
Especially, I mean, Fermi's is in terms of like neutrons and protons, so it's kind of
Right. So okay. So the answer is that in this limit, where the photons are long wavelength compared to the nucleus. You can treat the nucleus using something called the heavy particle effective field theory, which is just basically doing any heavy particle gives you the same limit. So you can take the Feynman rules for an electron or a muon, and you can take the muon mass to infinity, and you'll get the same answer for when the nuclei are very, very heavy. So there's kind of a universal behavior as particles become heavy.
Say HQT or something.
HQET, that's correct, yeah. So HQET is the famous example that was first worked out, but there's also something called NRQED, similar thing. So, okay, so what I want to tell you is that we should do both of these parts together, right? We want them to come from the same theory. And we want things to be systematic and well-defined, and we want it to be a field theory. That's what I'm trying to pitch to you, okay? And that's basically what we've done in these papers, okay? And we want to separate scales to minimize theory error. I'll just show you this cartoon. So there's all these scales in the problem. And today's talk is about this lowest energy scale. And so I'm going to try and explain to you how you construct an effective field theory to deal with these scales, okay? Order 10 MeV. So it's called EFT5 in this thing, but it's just some effective field theory. And the power of this method is basically you can think of trying to compute everything all at once. I don't know, in a microscopic quantum field theory, and that would be like dealing with this tangled ball of yarn. But if you can pull it apart thread by thread, right, you can solve each of these problems one by one. And that's basically what the machinery of this effective field theory framework lets you do. Good. So, this is in the language that I'll use that I will try to avoid, but may slip into. So this might be helpful in case you need a Rosetta Stone. What we expect is that all of the higher scales that I showed on the last slide, everything from here and above, can just be absorbed into a coupling constant, a coefficient. So I call that a Wilson coefficient, this C naught. It can depend on other scales in the problem, but I've just used the nuclear radius as an example. Okay, so there's now a number that depends on the nuclear radius. And then there's some matrix element, something I can compute with diagrams in a low energy effective field theory. Okay, and there are corrections to this formula that are suppressed by this PR thing. So these would be power corrections. Okay, I'm not going to talk about them until very close to the end of the talk. I'll just mention what should be done. If I have time, maybe I won't. But the point is, everything I'm going to tell you about is that quote unquote leading power. So just in the limit where you drop all the terms that go like PR goes to zero. There's a good reason for that. I'm going to work to like very high order in QED. So like 3 loops and above. Okay, and you only need to do that if you're talking about the largest corrections. So if I had a power suppression, PR, I wouldn't have to work to so many high orders in QED because the number would already be smaller, right? So the leading power stuff is where I have to work the hardest at all of this loop business. So you can think of this as short distance physics, factorizes multiplicatively from long distance physics. This is universal. This depends on nuclear structure. Okay, so what I want to convince you of is that actually this whole box corresponds to this effective field theory matrix element. And that actually, just based on what we know about how quantum field theory is factorized, all of this other stuff, so if I multiply this inner radiative correction up, right, all of this other stuff will factorize and be absorbed into what I call the short distance coefficient. So we're never going to deal with this. We're just going to assume that it's like I bring it down with tablets from a mountain, okay? And it's just, I have it. This is what is going to actually be computed. Okay, so to give you a rough, the punchline before I get into details, the black line, so this is radiative correction, okay? The black line is us taking what's in Towner and Hardy, where they use Serlin's quote unquote heuristic estimate for one part of the radiative correction. And so we just take what's in their paper and we plot it. Okay, and this is the radiative correction they apply as a function of nuclear charge. What are shown here in the red, blue, and then eventually green bands are basically where we count Z and logs as if they're about 10, right? So 10 is like 1 over square root alpha. Okay, so we just assign those numbers a formal counting with respect to alpha. And so that's how you get funny terms like order alpha to the 1/2. So that would be like alpha times log is in this counting order alpha to the 1/2. Or Z alpha is alpha to the 1/2. So we just keep terms at higher orders in this expansion. And then the band is obtained. One of the advantages of doing things in quantum field theory is that you can vary scales. You can vary your renormalization scale and get an estimate for the error. So the bands are obtained by wiggling a renormalization scale, which gives you an error estimate. So it's already an improvement compared to what's in the literature. We can actually estimate errors. Okay, so in doing this error estimate, okay, what we find is that at reasonably low Z, so the largest Z you would need for super loud beta decays is out here, we start to see convergence between the order alpha and order alpha to the 3/2 result. Okay, so starting to lie on top of each other. And what we also see is that there is a large discrepancy with what's actually used for the outer radiative corrections in the CKM unitarity stuff. And this goes in the direction of actually resolving, it doesn't completely remove, but goes in the direction of resolving the CKM unitarity puzzle. Okay, that's kind of the punchline. But I don't want you to draw premature conclusions because there is a part of the matrix element or a part of the radiative correction that we should really be including here in this green band that we don't have and which we've just assumed is the same as what's in this what's in Towner and Hart. Okay, so we basically there are certain pieces we can. I told you there's coefficients. You can ask if you know them. We've changed all the coefficients that we know the answer to, but there's one that we've like left as is in the existing analysis. But nevertheless, this certainly suggests that outer radiative corrections have a much larger theoretical uncertainty than what was assigned to them in existing CKM unitarity papers. And so this is important to revisit.
So sorry to interrupt, but you showed that there was some theory error on the VUD.
Right, it's basically, this is totally negligible in that.
Okay.
This is, so all of the outer radiative corrections are assigned a theory error of like nothing.
Okay.
Like 10 to the -4. So 6 times smaller than what the end result is.
Mm-hmm.
Nucleus by nucleus, it can be orders of magnitude smaller. The largest uncertainty comes from the nuclear structure contribution. And so groups I told you are working to like beat that down. So what happened is that there's an old way of estimating the nuclear structure that Hardy and Towner were doing. Hardy and Towner are by no means precision theorists. They're yeah, anyways, but they've done this great job. I think one of the hardest things about this problem is that there's so many moving parts, right? And so they were able to do a very good job of synthesizing all of the different pieces together into getting comprehensive fits to kind of global fits to all these super loud beta decays. There was a paper in 2018 that came out from Misha Gorstein, Chen Yaseng, and Michael Ramsey-Musoff, which pointed out a deficiency in how the nuclear structure was handled. And then they gave the crudest estimate they could think of, right? And assigned a gigantic theoretical uncertainty to it because they didn't really try. But they said like, okay, you missed this basic physics. Let us try and estimate it using a Fermi gas model. If you know what a Fermi gas model is, it means you put a bunch of fermions in a box and you say that's a nucleus. Okay, so it's by no means realistic. And they said, okay, therefore we're just going to assign a 40% error, 30% error to what we got. So that can come down, right? So there's, but so the point of this work is in part like, you know, are you really understanding that there are certain pieces of the puzzle that are extremely well defined, and this is one of them. This is all in principle just QED, and so the statement is that the error. So what they did to assign an error to this is they took the term at, I think, Z squared alpha cubed, and they multiplied it by 0.3. So they just took this coefficient and said, that's the last one, that's the highest order, and it's just in a footnote of Serlin's paper. So they used to do, I told you this in your office, they used to do ±1 times this, now they do ±0.3.
Just made up, right?
Yeah, right, it's just made up. This is not just made up, right? This is, I'll explain how you get these curves, hopefully at some point in the talk. And if not, I can show you offline. It's in the talk. I don't know if I'll get to that part of it. Okay, so there's like 20 minutes left. So, I think I'm gonna emphasize this because this is really the structure. And then we could do pick your own adventure. I could tell you more about how the Fermi function actually, you can derive it from diagrams. Okay, or I could tell you a bit about this part, which is how you use, once you know that it's a quantum field theory object, how you basically use renormalization group techniques to predict all the coefficients of many logarithms at very high order. Okay, so I'm gonna talk about this and then I'm just gonna poll the room. So think about what you want to hear about and you can raise your hand. Okay. So you said HQAT, there you go. It's on the slide. You predicted it. You get a prize. The idea is to use heavy particle effective field theories. And if you've ever heard a talk about effective field theories, there's kind of a history to the subject. So the zeroth order history is that you integrate heavy particles out. So you match from a theory that, say, has a top quark onto a theory that doesn't have a top quark. And you adjust all the coefficients in the theory and you introduce higher dimensional operators so that the theory without the top quark for all scales below the top quark's mass reproduces the theory with the top quark. Okay? And it turns out there's basically little theorems you can write down that say you can always do that. Okay, the next level of sophistication is this one, where you have a heavy particle in the theory that you want to integrate out, but you can't get rid of it because it's like in your reaction. So like a nucleus is very heavy, like lead is 200 GeV. So I should be able to take advantage of the fact that it's very heavy, but I clearly can't integrate out lead, or I wouldn't have any lead in my theory, right? I wouldn't have a field that's called lead nucleus, and I wouldn't be able to I wouldn't be able to write a scattering amplitude with it. So the idea of a heavy particle field theory is you don't quite integrate them out. You integrate out the antiparticle of the field. So if I have a nucleon, I integrate out the antinucleon. If I have a proton, I integrate out the antiproton. And all that's saying is that if I have a proton in my theory, that's okay. But the energy scales of the problem are such that I'll never create an antiproton, right? So I can at least get rid of that part of the theory. And when I do that, it turns out things simplify a lot, and it manifests certain symmetries that appear in the heavy particle layer. So the basic trick is like you take propagators like this, like you've maybe seen in a quantum field theory class, p squared minus m squared. This has been kicked a little off shell by some momentum k. And if you expand in the limit that m goes to infinity, p squared cancels with m squared, right? So the first term is 2p dot k. Right, and so this just reduces to 1 over v dot k, where v is just the form velocity of the heavy particle. So if you have a particle in the lab frame, okay, so a particle at rest, v is just 1, 0, 0, 0. So this is just 1 over energy, as in this is the kind of term you get when you do perturbation theory and non-relativistic quantum mechanics. Okay, so in some sense, this is just a way to do non-relativistic quantum mechanics but set up like a field theory. Okay, the other simplification is that in QED, we have things where like a photon couples to gamma mu. You have to remember all these gamma matrices, it's a lot of work, it's no good. Instead, if you have a heavy particle, it turns out that it dominantly couples to one component of the scalar field, or sorry, the vector field, the photon. So it dominantly couples to A0. So this is what you would expect, right? In a non-relativistic limit, you mostly couple to Coulomb. The Coulomb field is dominant. Transverse photons are less important. Okay? So in the end, you can write down the point-like effective field theory that I'm defining here for nuclei. Okay, and all I'm doing is I'm taking heavy fields, A and B, that are, as far as bit theory is concerned, they're just heavy sources. They're just heavy particles that move through the diagram. They can never be created or destroyed, okay, except for by this external operator. So the way you think about this is that a Lagrangian And the Lagrangian says the A fields are always there and the B fields are always there. And there's some operator I stick in that destroys an A field and makes a B field. So that's the weak current, right? So that's because it changes the charge of the particle. And then I just have QED and neutrinos. Okay, so then I can just draw graphs like this, right? Which is a big mess. But the point is the Feynman rules from the graphs just come from this. And the rules are that A and B only couple to A0. Okay, they only couple to the zero component of the QED field, the photon field. And the electron couples just like it does in ordinary QED, like the rules you find in Peskin and Schroeder. Okay, so the idea is that if you analyze a graph like this, it has lots of different bits in it. So because maybe the next thing is better, because the initial particle and final particle have different charges, this graph is really of order z times z plus 1 squared, right? Just because like look at where the photons talk to the particles, you just pick up their charges. And so if I just expand this with the binomial distribution, or I just expand it, it's just squared. I get a term that goes like z cubed, I get a term that goes like z squared, and I get a term that goes like z. So this is leading in z alpha. So it's 3 powers of z, 3 powers of alpha, because alpha goes like e squared. So this is what we call the Fermi function. So this graph is somehow contributing to the Fermi function. Okay, and then the subleading stuff is what we call outer radiative corrections. Okay, and if we want to divide out by the Fermi function, we want to compute stuff and then divide out ft, we need to know how it shows up. If we want to get some, if we want to be able to compute this 1 plus delta r prime, I need to kind of compute the whole answer and divide by this thing. So I need to know where this thing comes from. Okay, so show of hands. Who is most interested in hearing about how this Fermi function thing arrives? You have to vote for one of the two, by the way. No silent votes. Okay, so the Fermi function shows up in as a bunch of diagrams, and then the other option is who wants to know how you predict all of these coefficients with logs in front of them. So option 1, the Fermi function thing. 5, 6. Okay, and who wants to know about the other one? 1, 2, 3. You didn't vote. You didn't vote. What are you voting?
Majority.
Okay, so we'll mostly talk about this. At the end, I'll flash some. I'll go through the other thing like machine gun fire. Okay, so I think this is the more interesting thing, by the way, conceptually. So you can read the papers if you want to know the impact on extractions of UD, or you can talk to me afterwards. But let me explain how to think about this. Okay, so if I want to understand the Fermi function, I only need the leading in Z re-summation. So I can just take all those graphs and everything else. I can just drop everything that's down by a power of alpha. Okay, so to review, you'd solve the wave function, you find out it's divergent, you don't know what to do. Okay, you put in a regulator, but if you've ever taken quantum field theory, you know you're supposed to regulate and renormalize. This is like a problem where people have just been regulating and not renormalizing. So the basic, one way you could phrase this is how do you properly renormalize the Fermi function? Okay, so there's pros though. If I solve the wave function, I manifest that I have universal Coulomb physics that shows up in the point-like limit. I can solve this for a point-like Coulomb field, right? Whereas the way people deal with this otherwise is they put in a nuclear potential, and then you're always like kind of wondering like what parts are universal, what parts depend on the microphysics, how do I separate those? And this resums the series to all orders in Z alpha, which is basically a requirement for this problem. So that's what's technically challenging about this. Okay, you can say all these whatever fancy words you want about loops and stuff, but the homework is really to resum the full series to all orders in Z alpha. So that sounds very hard. The cons are that it's regulator dependent. So like, is this even physical? What are we doing here? And there's no clear way to interface with short distance physics. Unless you just compute the full answer and then divide things by some conventional choice. So this is convention dependent. So there's clear cons, right? So what about if we just compute diagrams? So you can do that. We did it up to 2 loops and you get this, and it's not very informative. I don't know how to guess what the next order is, right? If you do, you're a savant. I'm very impressed, but I don't. So I'm going to claim resummation is impossible by brute force. So the question is if you can have your cake and eat it too. So what you want is a renormalized amplitude. Okay, but you also want something that's all orders in ZL, right? So this is like, if you're a real stickler, you're a particle physicist or somebody who really likes field theory, you get really hung up on this, right? But if you want to make a phenomenological impact, you need the right? So how can you have both? And the answer, okay, is actually just comes down to like a little thing from your grad quantum mechanics class. So I hope everyone can follow this part of it. So the way to make the connection is to ask, what was that wave function we were computing anyways, right? Like, how do I think about that in perturbation theory? All the diagrams are in perturbation theory. Maybe if I can just understand what the wave function is in perturbation theory, I can make some progress. So what you should realize is that we know how to talk about scattering state wave functions in perturbation theory. We just use the Lippmann-Schwinger equation. Okay, so this is just the Schrodinger equation written in a funny way, right? And so what it says though is that a scattering state is like a plane wave plus the firstborn approximation where I insert the potential once and I have a propagator, or I insert the potential, I have a propagator, I have a potential, I insert the propagator, et cetera, et cetera. So that's great. What is psi p of x? Okay, that's also easy on the left-hand side. You just sandwich it with a bra on the left of coordinate x, right? And now it's actually not so hard, right? I have this expression on the right. I can put an x on each of these terms, and I can insert complete sets of states in various places. Any one of you can do this if you just take 30 minutes in a room, and because I'm not going to actually compute the integral at this stage. I just need to get this expression. Okay, so this expression, this came from the propagator. This is the Fourier transform of the potential. And notice I get this funny e to the iq dot x. So outside I have e to the ip dot x. And where's this coming from? I get e to the ip dot x from this because that's just a plane wave. That's what that means. Now here, I start with some state that has momentum p, but I kick it with momentum q from the potential. So the state on the other side has momentum p plus q. So when I hit it with a position eigenstate, I just pick up e to the I p plus q dot x. Okay? So all I'm saying is just that I pick up this. Okay, and if I kick it multiple times at higher orders in perturbation theory, where, so I'll try to make this really clear, where I have photons that come in like this, Q1, Q2. Okay, so then there's this thing, if this has momentum P, this is a momentum P plus Q1, P plus Q1 plus Q2. Okay, the term I pick up in the end is always this one. So, okay, so it turns out that if you wrote out the Feynman diagrams and you just did them, okay, you would get this at leading order in the Z alpha expansion without that funny phase factor, right? So what's going on? This phase, right? We know what it means here. This wave function blows up as I take r to 0, as I take the radius to 0. And if I keep r finite, clearly I'll get a finite answer. What's it doing in the loop? Okay, so I call this a loop because I integrate over some momentum. But really, you can think of this as inserting complete sets of states if you prefer that language. As I integrate over 3 momentum q, when if x is very, for any finite x, when q gets very big, this oscillates wildly, right? And so this just damps out the integral at large q. So what's going on is that I have a finite distance regulator, if you like. Okay? So it turns out that because of these properties of factorization I mentioned earlier in the talk, I now understand that this wave function I can think of as an amplitude with some short distance physics. Okay, the short distance physics I stuck in by hand, I've just evaluated the wave function at some coordinate. But it turns out what that means is that this wave function will factorize into the different scales of the problem. So there's a soft scale, which is basically like if you put in a photon mass, you think of this like a Yukawa potential, or there's some atomic screening, that's this stuff. There's the scale of the beta decay, we'll call it hard. And then there's some really short distance stuff that depends on x. Now the amplitude we actually want to compute is this soft thing times this hard thing. And then there's this short distance stuff that depends on some scale of nuclear structure or some other high energy scale. The point is that these have to be the same. Okay. And what I'm going to do is use this to extract this. And then once I know this, I feed it up. Okay. So it turns out you can just, I'm not going to go through this, but you can just compute this thing. That's one of the novel aspects of this. We were able to compute it to all orders in perturbation theory. So instead of computing this to all orders in perturbation theory, I'm going to compute this. And it turns out to have special properties that make that easy. Okay, so I can get resummed expressions, and it just turns into this simple answer. And it turns out that the wave function indeed looks exactly like this. It has this non-trivial Dirac structure with exactly these coefficients. You can just check by solving the Dirac equation. And so that's like a non-trivial prediction of factorization, and it turns out to hold. Okay, but now I know all of these things to all orders in Z alpha. So it's a simple matter of division to get the one I don't know. Okay, so this is the answer. Okay, and what's cool is that this is the answer renormalized in MS bar, minimal subtraction, with like a renormalization subtraction point, like the thing that you learn about in a quantum field theory class. Okay, so I'm not going to dwell on this too much, but this is I think very cool. This is a all orders closed form solution to what this big string of amplitudes would be. And it's renormalized in the way that most people renormalize their stuff so that you can plug it in and use it with other things. So we can have our cake and eat it too. That's the moral of the story. Okay, so I'm going to just try and do this last part of the talk really quickly, but it's very important from the first part of it, from what I just showed you, that that thing depends on mu now, depends on a renormalization scale. Okay, and there's a tool called the renormalization group. Let's just skip past this, which lets you evolve things from different scales to other scales. So now it is not a solution to a wave function, but I can interpret this as like an amplitude in quantum field theory. Okay, and what that means in particular is that what's really going on is I have a Wilson coefficient that I've like kind of been not talking about since the beginning of the talk, but it's there and it depends on the renormalization scale too. And then there's an amplitude and that depends on the renormalization scale. And these need to conspire such that when I change the renormalization scale, this stays independent of the renormalization scale. The renormalization scale is just a bookkeeping device. This is a physical thing. So bits of this get reshuffled into here and vice versa. So what I would like to do, okay, is start from the scale where somebody gave me the Wilson coefficient. Okay, somebody told me, you know, what this looks like at a short distance scale. And I would like to evolve it down to a lower scale. And the reason I'd like to do that is that whenever I go to compute this, okay, you will always find things that look like log mu over p, okay, or 2p over mu. Okay, and if p is of order the q value and the reaction, right, p is the momentum of the electron. If I pick mu to be close to that value, those logs are never big. Those logs are kind of, you know, if it's exactly equal, that log is 0. And if it's a little off, they're going to average to 0, right? So what I want to do is I want to compute this matrix element at a scale where there are no large logs. And then what I can do is I can push all of the big logs in the problem into this Wilson coefficient. That's the strategy. And now I know how to do that because I know how the coupling runs in QED. And the one thing I need to know is how does my operator run in, and for that I need this thing, the anomalous dimension. So what I've told you from what I've told you so far in the story, well, actually you'll see, we know parts of the anomalous dimension, but not all of it. So the anomalous dimension, you can just write in total generality and some expansion like this. So you just expand it in alpha. At 0th order in alpha, it's trivial. So it's just 1, or sorry, it's 0. But at higher orders in alpha, there could be a piece proportional to Z alpha or just alpha. At next order, there could be alpha squared Z squared, Z times alpha squared, or just alpha squared, and etc. It's just all possible combinations of Z and alpha, where Z, the power of Z is never bigger than the power of alpha. Okay, so it turns out we know some of these things from from solving the Dirac equation, from what I just showed you, we know all of the leading and Z coefficients. And from existing literature on heavy quarks, we know all of these coefficients. So the only things we don't know are this and this. But one cool thing is we found a new symmetry in this problem that tells you that these are related and these are related. Okay, this symmetry comes from, if you imagine taking the electron and turning it into a positron, and at the same time you change the charge of the nuclei in the reaction. Okay, you can just kind of do that formally and look at all the amplitudes, and you'll find that they're invariant under this swap. And that basically tells you that everything needs to come in some combination that's like Z times Z plus 1. So that's where the symmetry comes from. Okay, so now if we want to make progress, we know everything up to here just immediately from results in the literature. We don't know this. We would need new input for this. But if we did know it, it's kind of cool. Then you'd know this, this, and this. You know everything at 3 loops. And you know this, and this would be your first mystery entry. So it's like you know the thing at 3.5 loops. So we computed that, and that's the number. Okay, and it involves computing these graphs. And it's kind of hard, but none of you need to hear about that. Okay, so that gives you this table where you know all these things. Okay, so that's fine and dandy, but pretty technical. It lets you, by just solving this renormalization group equation, get expressions like this, where I assign this counting that I mentioned earlier in the talk. And I solve the renormalization group equation that resums a bunch of logarithms, okay? And then I just Taylor expand the answer. I just tell Mathematica, like, please series expand this with these rules. And when I do that, I just get some explicit expression, which is organized in powers of, you know, if I assign this formal counting of Zs and logs are like 1 over alpha to the 1/2, these are organized in powers of alpha to the 1/2. Okay, so I could just keep terms at higher and higher order in the expansion. Okay, there's a limit to how much information I can get out of this, depending on how many terms in this table I know. So eventually, I need new input. Eventually, I'm going to need this number. But I'm going to tell you, we're never going to need that for super loud beta decays. So we already have, from this calculation, everything you'll ever need to know to evolve, to predict the logarithms, that higher order logarithms that you're going to encounter in beta decay. Okay, so that's how these curves are generated. And the point is that these curves depend on a high scale and a low scale of alpha. And since I've run that scale, right, I told you we should evaluate the low energy matrix element at a scale close to 2p. But, you know, exactly what that number is not totally clear. So you just wiggle that low energy scale here. That's how you get these error bands. You just take this expression. It has these things, AH and AL are like alpha at the high scale and alpha at the low scale. Okay, and you just wiggle the scale in the theory, right? Any dependence on the scale is indicative of some higher order correction that's supposed to cancel that dependence. So it's giving you an estimate about the next order in the expansion. Okay. So what's the impact on CKM? Just to review, you can predict these logarithmically enhanced terms all the way up to order alpha squared in this counting. So that means something that's like alpha to the 4 z cubed log cubed, something like that. So that's way higher order. Like the stuff in Towner and Hardy never included something that's like z cubed alpha to the 4, but we can actually predict that coefficient and include it. And we can do it in some well-defined power count. So you could also ask, if you change the power counting, you could make different predictions and you could compare those to data. So one conclusion is that some coefficients in the existing theory are definitely wrong. That's a conclusion. Including that term that's like z, maybe I didn't write it, but there's a term at order z squared. I'll write it here. This term is wrong. The literature, and we corrected it. Okay. And so you can get something like this. So you can define these outer radiative corrections in terms of things in this long distance effective point-like theory. And this term in square brackets, I've just written here, And you can expand this all the way up to order alpha squared in our counting. Okay. And when you do it, this is the thing that corrects the result in the old literature. But more generally, there's terms that just haven't been included, like this one and this one, which in our counting are the same size. Okay. So to give you an idea of how big of an effect, like numerically, this has, we can just take the difference of this z squared alpha cubed log term and compare it to the expression used in Towner and Hardy. And the differences range from kind of 10 to the negative 4 to 1.5 times 10 to the negative 3. Okay, so it's very big on the scale of CKM unitarity. And gigantic on for the size of like what they ascribe the error and the radiative correction. The definitive statement requires this order Z alpha squared matrix element, and this is definitive only for exactly what the outer radiative corrections are. There are other pieces of the puzzle for the CKM unitarity that need to be put in place. And so my conclusions and outlook, maybe this helps. If I have this power, these other power crowding parameters like isospin breaking, power corrections, et cetera, the story I've told you in this giant series, right? I have all these different coefficients with different N, M, A, and B. I've only told you a story about the terms that are like N, M, 0, 0. But I've told you the story at a very high perturbative order, which is nice because if I had these terms and they were raised to say the power 1, right, that would be an extra suppression by a factor of 10 or 100. And so, yeah, so stuff that needs to be done. There's interesting work to do for computing power corrections in this effective field theory I mentioned, or that I've given the whole talk about. I also think it's interesting to revisit the formalism for isospin breaking and radiative corrections to understand if they actually do factorize and what that looks like. Okay, and then this is my summary, and I won't go over it in words because I think I'm already over it.
Thanks, Ryan. We have time for a question or two.
You like motivate again the power counting and the logs. Like is that just a choice you're making?
Yeah. Maybe this helps. So a look at the so this is atomic number, so just divide by 2.
Yeah.
But kind of look at the size of Z.
Sure.
Log is typically like 5.
Yeah.
So you could argue, for instance, that you might want to count logs, not like 1 over square root alpha, and then maybe you would truncate earlier in the expansion. But one of the nice thing about RG is it lets you get a lot of these logs for free. So there's a sense in which you can systematically include them. And certainly what I can tell you is that if you organize the expansion in alpha, Z, and log, right? That's like a triple expansion. What this tool lets you do is predict certain coefficients. That's basically, you can say if this thing is going to be invariant under renormalization group flow, these are the precise coefficients you need to have. And so it's something you can include. And if, for instance, your suspicion is that the higher order logs are unimportant, you can just check. And if they are, then then they are, and that's reassuring. The higher powers in Z are kind of you have to compute, so that requires new input. You can't like get them for free. Yeah.
Maybe 2 questions. The first is you use MS4 to do this. But I mean, this is QED, so you could just do it on shell, so you don't have any like coupling. So it's just harder to build a higher loops for the on shell or something.
Well, it's a good question. You can express everything in the end in terms of the on shell coupling.
Otherwise, you would have no running coupling at all.
Yeah. So there's some disadvantages to that. So it becomes harder to do like error estimates. So you can ask how you come up with an error estimate for that. But at the end of the day, that's kind of how Serlin's old work is done in the on-shell scheme. But you're still basically using the same. You still can use the same renormalization theorems that allow you to predict higher order logs. So you can dress this up all in the on-shell scheme, but I don't think it makes. I think it just becomes a little more clumsy how you discuss the prediction of higher order logarithm or logarithmic enhancements. So in an on-shell scheme, you're still going to have large log.
We'll have large logs, you just want mu in there.
That's right. Yeah, but you'll still, so basically, if you do the on-shell scheme, you're going to force maybe there's another way to phrase this that can be most clearly done.
It seems you just have less
Here.
freedom there.
So if you do it in the on-shell scheme, you could also view that as just like choosing one mu and sticking to it the whole time. So then you'd have this thing, right? But then one of these two terms has to have large logs in it. Right? So in the way you're doing it, all the large logs would be, if you'd like, buried in here, except you'd only be on the left-hand side of the equation. So then you can ask, how do you fish out those large logs? Like, what if I'm worried about a thing that happens at fourth order in perturbation theory from 3 logs and 3 z's?
I think so, it's just easier to get the.
It gives you a way, yeah, this is just a way to, RG is like, it's a trick that lets you basically fish out, demanding RG invariance is a trick that lets you fish out logs in the problem. And then one other technical thing that I'll tell you that I didn't appreciate as a grad student, the other reason why people like mass independent subtraction schemes is it makes the beta function very simple. And that basically means that, so I don't have it here, I deleted the slide, but there's a closed form expression for the RG evolution. And in a subtraction scheme with a mass scale in it, like on shell, that's not true. So the differential equation is harder to evolve. Like, it's not impossible.
Maybe the second is for this wave function that.
Yeah.
Is this the wave function between the quarks inside the nuclear or between the proton or?
No. This is the wave function of the electron.
So this is the electron back reacting with proton you're trying to describe, or?
I wouldn't call it back reacting.
It was I was unclear why the wave function is.
Why it's important. So what do you find most informative, wave functions or diagrams? I can tell you either way.
How did it appear as like form factors? Like
No, it's not a form factor. No. It's
how does it appear in the problem match?
so. Well, maybe the most natural way to think about it is that when you evaluate a current inside a nuclear state, right? And then this is multiplied. We normally think of this as just multiplying some. Please tell me if this is opaque, by the way. If anything's confusing, just let me know. Let's do it like this. So you would often get something like this, where L mu is just like a bunch of plane wave factors, right? So this, maybe I'll make it more explicit. This is like, I'm going to have a neutrino and an electron in the initial state, or in the final state, or a positron. And I'm going to have my leptonic current, right? That has to make these particles out of the vacuum. Okay, so that's all at 0th order in QED. But this positron, if you wanted to include higher orders in QED, you could just treat this with a distorted wave. Okay, or equivalently, you could compute diagrams. So you could compute this diagram.
Like it's like something like that. You're just replacing it with like radiation coming off of it or something.
Sorry, you mean here? You're replacing E plus with a plane wave function, e to the ik dot x, with a solution of the Dirac equation in the background, Coulomb potential.
So you're just like trying to resum things into it.
Yeah, that's one way you can look at it. Yeah, and then you can kind of see what's going on, right? If R is small, right? And I can approximate this thing by its value at 0. Then I will just get something that looks like psi E bar. Let me make this an electron and that an anti-neutrino of x equals 0, where this solves the Dirac equation. Gamma mu PL V for the outgoing neutrino, because this is a plane wave. Like the neutrino is neutral, so it doesn't feel the Coulomb field. And so that's where that's coming from. That's where I approximate this by some highly localized thing. Yeah, but if you prefer, you could just sit down and ask, if I start including photon exchanges between this electron and the nucleus, what happens? Does that answer your question?
Yes. So I think you two may be chatting in a few minutes anyway, if I saw the schedule right. So right, yeah, so maybe we can, in the interest of time, end it there and thank Ryan again.
Listening.
Yeah, so. Thanks, everyone.